All right, good morning, everybody. Thank you for attending our AFT webinar. Hopefully you guys will find some value in this hour, especially if you've signed up, depending on where you're attending. Hopefully it's a good morning, good afternoon, or if you're international, maybe good evening or even good night. If you're watching in a recording, then we love to have you, and you can always come back and skip around and see some of the different features that we're going to be showing off here. I'm Nick. So I'm Nick Vastine. I'm a business applications engineer. If you've attended any of our other webinars, you might have attended one of mine in the past. Or if you've submitted a support question or a sales question, usually I'll be one of the first points of contact. So nice to meet you if we haven't met already. Today we're going to be focusing on visualizing results in AFT software. So the title of the webinar is "If you can see it, you can achieve it." A better title might be "If you can see it, you can analyze it." And then hopefully that'll help you draw better conclusions than solely looking at the numbers. So engineers, we can get very focused on the numbers, a little bit too focused. It's always good to take a step back, try to visualize results, see how it relates to the system before we try to make any engineering decisions. So that's kind of the big theme. It's going to be a pretty introductory level webinar, but hopefully you guys will see some new tricks that you haven't seen before that you can start incorporating into your own workflow. So if you can see it, you can analyze it. Let's go ahead and start jumping in. So first, we're going to go over the agenda of the webinar. It should be pretty straightforward. There's only so many ways that we can visualize output in AFT software. While I kind of rag on output a little bit, of course, it's a very valuable tool. And so there's some small changes that we can make using output control to make it an even more valuable tool for quick at-a-glance analysis, having AFT software do some of the work for you while you're checking these results. So this is largely going to focus in output control. We'll take a look at adding parameters. So we can either add new parameters or we can add redundant parameters that we can look at in different units. We'll look at something called junction deltas. So this is good if you have a bunch of pipes in series and you want to look at the total pressure loss across all of them without manually entering the pressure loss and summing them by hand. So we'll take a look at a junction delta, and then we'll also look at some initial design alerts. So a design alert, whether or not a pipe or junction in your system is meeting a certain specification, that'll throw up an immediate red flag. So that way you don't have to check intermediate values for each run. Those can be checked automatically. And if it deviates outside of those design parameters, then you'll get a notification. After modifying our output a little bit, we'll take a look at the visual report. So we'll compare an input visual report to an output visual report. Input is largely going to be used for double checking your input parameters and making sure that all the specifications are to your specification and no input error occurred. We'll take a look at an output visual report, which then associates all of those different results, now showing them where they occur in the system. So giving those results more context rather than just the spreadsheet that output can throw out to you. We'll take a look at some different selection tricks to make making a visual report a bit easier. We'll use the workspace selection and the select special features. And then finally, we'll conclude with a color map. So a color map is going to show how a parameter changes using color rather than quantity. That way, at a glance, you can look at something like flow distribution, as we'll be doing in this case. So again, how do you visualize results to make it not only intuitive to understand, but intuitive to explain as well? After we conclude visual report, we'll take a look at some of the graphing features. This is really the feature that I take most advantage of as I'm doing support cases or if I'm working on models of my own. Really, there's two big categories. There's profile graphs, which shows how a parameter changes across a flow path. Hopefully you guys are all familiar. We have some other selection tricks that we'll go through to make selecting those flow paths a bit easier. We'll show a stacked graph, which you can show different variables on their own graph with a similar x-axis. So a good way to relate how different variables are changing along that same flow path. Multivariable takes a stacked graph, but kind of combines the multivariable aspects into a single plot. A common application we'll see with that is hydraulic grade line and elevation. So seeing how much of the elevation change of the pipe contributes to flow compared to how much the static pressure will contribute. Finally, we'll take a look at a multi-path profile graph so we can compare different flow paths using the same graph and seeing how those parameters change in each. After we go through profile graphs, we'll actually take a look at a second model to explore pump and system curves. More specifically, we'll look at the new to Fathom 11 Arrow 8 feature about multi-scenario pump system curves. So it's a very clean way to show a lot of information and see the different potential operating points without creating a bunch of intermediate scenarios. So you don't need as many iterations to draw similar conclusions. Those are all kind of the steady state analysis and visualizing that we're going to look at. And then we also have some transient specific visualizing features that I want to go into. So this includes a transient graph, which just shows how a parameter changes over time. We'll show some animations. We'll animate both a profile graph as well as a color map. So building on that foundation of those concepts to kind of the fourth dimension with a transient. And then we'll also do a short aside with some multi-scenario graphing, which is also new to Impulse 8. So we have a lot of basic introductions. We'll make our first profile graph, and then we'll also find some of the more complex things that we can do once we're comfortable with that foundation. So before we get into it too far, let's first meet our models. The first model we're going to look at is a firewater system. So these are a bunch of spray discharges coming from a pressurized line. We're going to be taking a look at the flow rate out of each of these sprays in our visual report. We'll check that each of these pipes have a minimum flow rate that'll meet our requirements. That'll be one of our design alerts. And then we'll actually take this model and import it into Impulse, add a transient that all of these sprays are going to open at a certain time from a pre-pressurized line, and we'll see how that flow rate through the system will develop. The second system we're going to take a look at is really focused on that pump system curve. So it's a very specific example. It's a heat exchanger system where we're controlling the flow rate through each of these heat exchangers. We'll run some different scenarios if one of the heat exchangers is offline and we continue running the pump, how we may be able to change the pump speed to maintain close to that operating point, and some other comparisons between all those different variables as well. So what if this is closed and we speed it up? If it's closed and we slow it down? If it's open and we speed it up? All those different combinations can be summarized with one multi-scenario graph. So now let's take a look at output control. So this is what our goal is to make our output look like towards the end. So the first thing we're going to take a look at is a design alert. So at a glance, we can see if a criteria isn't met. So in our case, our design alert is going to be a minimum flow rate of 20 gallons per minute. So any flow rate less than 20 gallons per minute should be a red flag in our design. So these are highlighted yellow because they're not meeting that design alert. And so we'll go through how to specify that and how to apply it to the different pipes or junctions within the system. We'll take a look at redundant parameters and how we can add different parameters from output control. This can be helpful if you're sharing the model across different departments, which may use different units. For example, if you're not comfortable with barrels per day and you can really only think in gallons per minute, both of those things can be shown so you don't have to make a bunch of changes to the model when you're sharing it with a specific department, or if you're sharing it between offices, which may be international, you can have English units and metric units. Finally, we'll take a look at junction deltas, which we can see up here. So again, this is kind of summarizing different parameters, in our case, pressure loss, across a bunch of different pipes rather than trying to sum them up by hand. So that's everything we're going to look at in output control. So now we can take a look in the software and see what we can do. So here's our firewater system. Here's our pressurized line. Here's all of our sprays that we're going to be checking and exploring throughout this whole simulation. We can go ahead and run to get our output. And here we have our default output. So it's pretty plain. This is where you don't want to get stuck seeing all of these different numbers and getting used to just knowing, oh, I need to check pipe 236, I need to know the DP of that specific value. So the first thing we're going to do is add some design alerts so that way we can check for our flow rate requirements. There's a couple ways that we can do that. The first option is to specify it as you're creating your model. So if we go from within a pipe, we can go to the Design Alerts tab, and there we can open the Design Alert Manager. So this is where all of the different design alerts within the model are going to be created, not only the design alerts established for this specific pipe. Another way we can reach that is under Tools and Design Alerts. So that'll open the Design Alert Manager directly, indicating all the different designs alerts that we have specified for our system. To create a new one, we're going to click Create New Design Alert, very intuitive. We're going to specify a minimum flow rate that we're going to apply to our pipes, and that's going to be 20 gallons per minute. So here we have some different options for some different objects. So if we have a heat exchanger spec where we need a certain heat rate, or maybe it can check for temperature, as well as pumps. So maybe we need a minimum flow rate going into a pump to make sure it doesn't starve it, or maybe an MPSH requirement that we're trying to meet for the pump. In our case, we're just going to look at all pipes. We want to make sure there's at least 20 gallons per minute going through each pipe, because that's going to imply at least 20 gallons per minute coming out of each of these different sprays. So here we're going to set a minimum volumetric flow rate of 20 gallons per minute. We're going to add it to our list. And here we can add some combination design alerts if we're trying to really optimize our system. So let's say we don't want our volumetric flow rate to go above 300 gallons per minute. That could be specified in the same single design alert. So that way it's applying both of those conditions to each of the pipes that we're going to be selecting. In our case, we're only going to be looking at this minimum, so we can go ahead and remove that. Now we're going to update and add this design alert. Before we do that, we're actually going to select the different pipes that we want in our design alert. In our case, it's a very easy selection. We just want all of the pipes. And now when we add it, we can see that this design alert is applied to each pipe. So now when we run the model, it's going to be checking each and every pipe. It's going to check its flow rate, compare it to 20 gallons per minute. If it's lower than that, that'll throw a flag. And we'll see some of those flags here in a moment. One caveat is it will reset your results. So during the run, it's checking against those design alerts. You can rerun the model. And now when we take a look at output, we see a lot more red. We also see some highlighted values down in here. So the warnings that we're seeing are specific to the design alert. It's unlike a warning that you would see if you're having convergence issues. It's really just a notification to the user that these things may be of a concern in your model. Also see this giant red box at the bottom. Hopefully one of these will catch your eye, or this yellow in output to let you know that something isn't quite right, depending on how you're specifying that system. So now we can see at a glance which pipes are not meeting our design alert. And it makes it much easier to see if there's an issue, where that issue is occurring. So for example, if we wanted to compare, something else we can do is take this output tab and we can dock it to the right. Now we can see pipes 214 and through 218 are not meeting our requirements. We can go through here and see that these pipes are the ones causing the issue or causing the concern. So this is kind of like a poor man's visual report if we just split output and workspace, so that way it's easy to associate results with where they are in the system. We'll go ahead and add that back. And so that's design alerts in a nutshell. There's a lot of different things that you can add and a lot of different conditions that you can add. Something definitely worth thinking about incorporating in your system if you do have design requirements you have to meet and you're constantly checking. The next thing is actually specific to output control. So now we're going to take a look at adding some different parameters. Here in output control, accessed by the pencil in the spreadsheet in the top left, we show our different output variables. So here we can see we have volumetric flow rate, velocity, pressure static maximum, matching the output columns here. So we can easily rearrange these. If I don't care about volumetric flow rate, I can move it back. I can move it up as well if I grab here and move it. or I could remove it entirely. In our case, we're actually going to double down on volumetric flow rate. So rather than reporting it once, we're going to add it a second time. We're going to move that to the top. So here's where we can add a redundant parameter to kind of reflect a secondary set of units. So again, if we're sharing the model, it may be convenient to also report in gallons per minute and cubic meters per hour. Now, if we click OK, we can see both of those columns appear, and both of them are highlighting the values that have the design alert. So it doesn't matter what units you're defining the design alert in. If it's not meeting that criteria, it'll always give you a flag. So this can be a good way to clean up the different parts of output. So let's say your model is completely flat and you don't care about elevation at all, or any of these other variables. You can highlight all of them, remove them, and then that will also simplify the points that you care about within output. So that's how you add parameters, how you can remove parameters. You can also change it for different components like valve summaries, but those are things that we won't really get into. Output control is definitely something that I would recommend going in and experimenting with and just poking around, seeing what happens. Especially if you optimize your system, you can also save it as a format and then load that into your other models, so you're not always stuck getting all of the reports how you exactly want them. So that is adding and removing parameters, adding redundant parameters in different units. The last thing I want to show with output is this junction deltas. So now we're looking at the differences between an upstream junction and a downstream junction. This is actually another good place to split the workspace so that we can see our model. So we're going to be looking at the pressure differences from this junction to our final upper spray, and from this branch point to our final lower spray. So I want to know the total pressure drop from this branch all the way to this spray. We can do that with a junction delta. So our first value is going to be the inlet of this branch, and our outlet is going to be this upper spray 240. We're actually going to use the inlet because I care about what it is at this point. If we set it to the outlet, it'll actually just set it to atmospheric since it is a spray discharge. We're going to look at the change in static pressure, but there's some other parameters that we can consider. Pressure change is usually the most common. And now we can also add a second junction delta for these lower sprays. Great. Now if we hit OK, now it is totaling the pressure drop across all of these different pipes from this junction to this junction very conveniently, very centrally, rather than trying to figure out what pipes are in the path and then manually summing their change in pressures. So those are junction deltas. Again, kind of another feature within output control. Definitely recommend taking a look and digging around in there to see if you can set up your output exactly how you like it to speed up your analysis. So now, in review, we looked at design alerts, how it highlights at a certain specification, our redundant parameters, how we can add another flow rate, and then finally our junction deltas, which is exploring parameters across different pipes rather than trying to sum them manually by hand. So that's everything with output. Now we're going to take a look at visual report. So visual report personally is something that I underuse, but it does create a lot of value by associating quantities with their location in the system. And it can show a lot of information if you build them effectively and efficiently. So if you wanted to print this out, then that would also be good or contributed to a report rather than including the model and including a table of data that someone would have to manually link together. So within visual report, we're going to take a look at some selection methods. We're going to see how we can quickly select objects like all of these spray discharges and how we can use that to selectively apply data and what information we want to show. As I mentioned, we'll take a look at the difference between an input and output visual report. So an input visual report can be used to check lengths and nominal sizes to make sure the model is specified as intended, whereas an output can take the results and quickly associate them with their position in the system. Finally, we'll create a color map. So all of these colors are describing flow rate. So we can see the very high flow rate coming into the system, the initial branch, and how these flows are changing as they go through the system. So again, at a glance, how can I see how these parameters are changing rather than looking solely at individual numbers? How can you look at the behavior or the trend of the system? So these are the three things: selection methods, input versus output, color map. All those we're going to take a look at in our visual report. So back to our model. Now if we load visual report control comes up immediately. So we're going to determine which variables we want to include in our report and also which pipes and junctions we want to show that data for. Up here on the left is the difference between an input and an output visual report. I believe they're saved independently, so you can create an input and load it, and save an output and load that. Similarly, you can create a visual report template. If you know what parameters you like, you can save that and load that here as well. With an input, we're going to take a look at the lengths of the pipes, and we also want to look at their nominal sizes. We won't worry too much about the junctions because something that's easy to do with visual report is include way too much information that it's hard to really dive in, and it just muddies up all of the different quantities that it's trying to report. So we'll keep it relatively simple. We'll look at lengths and nominal sizes, which will still be quite a lot for the size of our model. And under show selected pipes and junctions, here's where we can select which pipes and which junctions we want to show that information. So for example, because we're not reporting anything on junctions, we don't have to show their junction numbers, and we also don't have to show their data. Since we're not choosing any data, this is unnecessary, but it may be good practice. And then on the pipes, we want to show all of their numbers. If we name our pipes, that may be important, and we can also show the data associated with them. Some of the other tabs on visual report control include this general display, mainly changing things like background color, or if you have a title and a legend, you can show those and vary the size of those as well. So we're going to look at lengths and nominal sizes of all of our pipes, and we're going to see what that looks like. So here we can see if we zoom out, it's quite a bit of information. And so this is one of the caveats with visual report, is it does take some additional effort to rearrange and make it readable. That's why it may be good to, one, make the text smaller, which you can do up here. So we can decrease the font. That makes it a bit easier to zoom in and read. So we do recommend viewing it online or within the software rather than trying to print it out, which may cause issues. But rearranging all of these, it can also clearly show which information is tied to which pipe in the system. So over here, we have a pretty good readability. We have all of our different lengths as well as all of our nominal sizes. So this makes it easier for someone to check all the different pipe lengths to make sure that they are to these specifications that we've detailed. So that's an input parameter or input visual report. All these different parameters can be graphed. So if you include all of them, you can imagine that it'll get pretty unruly to try to read. Obviously, we don't recommend doing this, but maybe you can create several visual reports showing the different parameters that you want. So now we're going to take a look at an output visual report. So here, rather than looking at pipe output, we want to look at the volumetric flow rate through our sprays. So now what we're going to do is we only care about flow through the sprays. We don't really care about the flow through the pipes or anything else regarding the pipes. We're going to change that and update that in our Show Selected Pipes and Junctions tab. So now on the left, we can select all of our pipes. We won't care about the pipe number or the pipe data. And on the right, so with the junction displays, we really only want to show the sprays. So one thing we could do is manually go by hand and select them all, or we're going to start using some of these selection tricks. So the first one is this special. So special is how we can make a selection according to some additional filtering. So when you select special, you can again have the typical selection. You can select all of them, none of them. But up here, our selection type gives us some more options. So you can do number range. So if you numbered all of your sprays only from 100 to 200, Like if we were only looking at the bottom half, then you can select that way. I guess it should be 199 in that case. Or in our case, we're going to be looking at junction type, and we're going to be only looking at spray discharges. So now we can see all the spray discharges. All of those are selected because I only care about the flow rate through those different sprays. Great, so now this is selected. Now if I select number and data, it should only show the number and data of these sprays. Now if we hit show, now we can see it's a much cleaner graph. We can see the flow rate through each of these junctions at a glance rather than having output and workspace on either side and trying to match them up manually. So that's our first selection trip. That's kind of the differences between input and output. Now we're going to go ahead and create a color map. So we're going to create a color map for flow rate. Again, we're going to go to Visual Report Control, and now we're going to use this color map tab. So here we are going to color the pipes, and we want to graph based on volumetric flow rate. This auto color map may be helpful if all of the flow rates are relatively close. So if we hit generate, we can see that it will create an even distribution. If we hit show, we can see that all of the pipes are colored, but based on our legend, it's not super informative how the flow is distributing. We just know all of these flows are relatively low, these are relatively in the middle, and this is a particularly high flow. So something we can do is adjust our color map, use this as a baseline, and then use a user color map to redefine these different values. So in our case, I want more resolution at our lower flow rates, which we'll go through and specify. And then towards the higher end, I want a bit more resolution, but not nearly as much as I'm getting down here. So great, now we have our new color map. If we click show, we can see it's recolored and we get a little bit more resolution in how the flow rate is changing. So we can see we're more than 650, then we're more than 300, and all the way down here is where it's more than 150. And so you can do this with all sorts of different parameters as well, like volumetric flow rate, flow velocity if you need that, the pressure loss through each pipe, so that can be informative if one pipe is causing an unnecessarily large pressure drop, that might be able to reveal that. Length, which I haven't experimented with, but could be cool. So all these different parameters, you can create the same kind of color map to show at a glance how these parameters are changing and how they relate to the system. So that is color maps. We'll take a look at how we can animate this for transient analysis. So it'll show how the color of the system changes as the flow rate through it changes through a transient event. Great. So that was everything I wanted to show with Visual Report. We looked at selection methods with that select special, how we can select based on junction type or number or all sorts of different parameters. We took a look at input visual reports versus output visual reports. So the different intentions and how we can specialize them for different types of checks. And then finally, we can take a look at the color map, which shows intuitively how parameters are changing through the system, whether you're using the automatic color map or a user specified color map to create additional resolution where you need it. So that's everything with Visual Report. Again, a good place to play around with your own models. We're trying to learn kind of features and individual things. You don't have to do it exactly how I do it, but as long as you know the feature exists, then you're free to go and experiment. So that's everything with Visual Report. Now we'll take a look at our graphing features. So the first type of graph we're going to look at is a profile graph. This is kind of the most level of complexity that we want to look at with this specific graph. So here we have a stacked graph because we have two different graphs sharing the same x-axis. We have a multi-parameter graph because we're graphing both HGL and elevation up here. And we have a multi-path graph, so we can compare the path of the upper sprays compared to the lower sprays for flow rate and hydraulic grade line. So this is kind of the most complex profile graph you can add. You can, of course, add a bunch more scenarios or a bunch more flow paths or a bunch more parameters all to a graph. But it's important, again, to make engineering decisions, see what makes your analysis most intuitive to not only understand, but to explain as well. So now, back in our system, we're going to take a look at our upper flow path. So we're going to make some profile graphs from this initial pressure point all the way to this final upper spray. So one way to do that is we could highlight each pipe because we want to select the profile that we're going through. For a small model, that may not be a lot of work. Maybe in here it may get more tedious. But a better way to do it is to use one of our other selection tricks. So here we're going to select our starting junction. We're going to select our ending junction. And now if we go to Edit, Select Shortest Path, following the direction of the flow path, now it's selected automatically for us. So that's incredibly convenient, way better than trying to highlight, which I'll be honest, I've tried to do in some support cases where there was a lot before I knew about this particular feature. So now when we go to Graph Results, we'll open up our Graph List Manager. And if you're brand new to AFT software, you can also take a look at this graph guide. So let's say I want a very quick and simple profile graph showing how the values are changing with the pipes. This will show which pipes I need to select, how I can select the parameters, and then finally generating the graph. It'll also take a look at some of the more advanced options. So in our case, we only have a profile graph available since there's no pumps in the system, but here we can create all sorts of graphs automatically for us. So here we can add parameters to create a stacked graph and really just outline the different instructions. Since you guys are all here, you'll all be experts by the end of this and we won't need this graph guide. So here, remember we have our selection on the workspace. Now we can use that to our advantage with this profile. So now if I select workspace, I don't have to remember which pipes are which. I can select them very easily and now generate our first profile graph. So here we have a static pressure graph. If I wanted to show a redundant unit, I can include the same variable, inset it one so it'll be on the same graph, and then change the units here. So let's say I want to look at it in bar absolute. So now it'll show the same plot, but now it's easy to read no matter what unit set the person is reading in. Something else we can do is show different variables in the same graph. So now let's say we have hydraulic grade line and elevation. So elevation is going to contribute to hydraulic grade line since that's helping flow go in that direction, but it'll also account for the static pressure. So a higher static pressure makes a higher hydraulic grade line, even such that it can overcome elevation, kind of the whole point of adding a pump. So here we can see at the very beginning, we have a lot of static pressure and not a lot of elevation. Whereas here our static pressure is reduced and elevation still has some contribution to the hydraulic grade line. So this could always easily flow down to 0 feet in elevation. So this is kind of a multivariable graph on a single graph. If we wanted a stacked graph, we just have to add a parameter and now we can graph those two things separately. One convenient thing is if we use this crosshair, it can tell us individual values, and it'll also show down here on this graph where those changes are occurring. So something that can be useful is if you have flow over a hill and you start seeing static pressure recovery, you may be able to compare elevation on the bottom and static pressure on the top and see how those two things move in conjunction because they're inherently related. So those are stacked graphs, and those can also be multivariable graphs. So if we again inset this, and now we can look at volumetric flow rate as well. Now we can have two stacked graphs and two multivariable graphs. Again, it's not necessarily the usefulness of this particular analysis, but how do we build a tool set and understand what we want to show in our analysis and show it very easily. If I found this graph incredibly useful, it's the only graph I ever need to generate for my analysis. I can also add this graph to a list. I'll call it profile graph. And now any changes that I make, let's say I make it megapascals, then I can always reload this graph and I'm always all set. So if I wanted to load this for a different scenario, for example, we could do that very easily. So it's nice to just make a graph once, make it exactly how you like it, save it as a graph list item, and then you can load that for your different scenarios. So now the final part, we've talked about multivariable, we've talked about stacked graphs, and we've talked about creating a profile graph in general using that workspace selection. Now we're going to be looking at a multi-path graph. So here we can select multiple paths using groups. We have a group that exists in the system already, but we want to take a look at the difference between our upper spray path and our lower spray path. So to do that, we're going to go back to our workspace. Luckily, this is already selected, so it's very easy to make a group from this selection. We'll go to Edit, Groups, Create a Group, and we're going to call this Upper Sprays. So it'll include all of our pipes, all of our intermediate junctions. You don't necessarily need the junctions for what we're doing, but it's a good practice to include them as groups. We can hit OK, and now to create our lower paths, we're going to do that same selection trick. Edit, select shortest path, select it that way, and then create a group in the same fashion. This time, lower sprays. We can hit OK. So now we have our two groups. We can use that to select in the model as well. Under groups, select. Now I want the upper sprays. Very easy to do that, especially if you have a more complicated model. But now in our graph results, when we go to plot multiple paths, now we see those groups are available for our use. So we're going to go ahead and simplify this a little. We're going to look at just volumetric flow rate. We'll look at the HGL elevation comparison between these two spray paths. So we're going to look at both of them. Now if we hit generate, we can see there's a little more information included in the legend. We can see the upper sprays and the lower sprays and the variable that we're graphing. We can also see how the volumetric flow rate changes. So they're the same where the flow path is the same, and then as they split off and branch out into our different spray discharges, obviously the flow rate is going to go down. Something else we can do here is adjust formatting. So here you can look at these specific graphs. You can change how the plot lines are specified. You can shorten legend titles if you want. And so this is another place where you can go and experiment with these formatting options and then save them as a graph, and they should be saved. So that's profile graphing kind of in a nutshell. We took a look at multivariable, as we mentioned, multi-path in this case, stacked graphs, and just profile graphs more generally. So that's everything that we wanted to show with this model. Now we can do all of our necessary analysis on the system rather than just looking at these different output values. Great. So again, we have our profile graphs. Our second type of graph is our pump system curves. So now we can look at them for multi-scenario graphs. I actually wrote a blog about how to use this multi-scenario feature, which is attached here in this webinar. You can download it under handouts, or you can try to find it in our tips and tricks blog on our website. So if you guys like webinars and you like finding new and unique ways to better improve your modeling processes, then I would definitely take a look at those tips and tricks blogs. We try to put out one every month, and we love your feedback. If you have ideas on what you want to blog on, you can also give us a shout and we'll try to include them in our list. So here we're going to take a look at a multi-pump system curve, multi-scenario pump system curve, where we're going to look at how system curves change based on changes to the system and how the pump curve can change based on changes in speed. And so to do that, we're going to take a look at our second model. So here we have a very basic pump system. This is specified with a pump curve. And we have some additional input to include our best efficiency point, as well as our preferred operating region and allowable operating region. This is something we've discussed pretty in depth in another webinar called 3 operating issues you can try to solve with Fathom. So exploring what BEP is and how it works, if you're at all interested in making sure your pump runs both well and for a long time without a lot of downtime, definitely worth taking a look. But we can include this on our pump curve to see if we're falling within those recommended regions. So we'll hit OK. In our case, we want 25 cubic meters per hour through this heat exchanger and 25 cubic meters per hour through this heat exchanger. We go ahead and give it a run. We can take a look at our output. Based on our valve summary, we can see that our volumetric flow rates are 25. So that can be a good place for a design alert. If I want it between 20 and 30, that's my allowable deviation. That can make a great design alert through these valves. Here we're going to focus on graph results. So before, when we were looking at the firewater system, we only had this profile graph option. Now that there's a pump in the system, we can generate a pump system graph. So here we're going to show the pump curve as well as the allowable operating region and the preferred operating region. If we hit generate, we can see how our pump curve comes down and our system curve comes up as friction increases with higher flow rate. Where they intersect is our operating point, pretty much exactly at our 50 cubic meters per hour. We can also see our preferred operating region and our allowable operating region. In our case, if I want to make this a bit bigger, I can use user specified flow rate range, regenerate, and now I can see more of the graph. So that's a very basic pump system curve, very limited things to input. It can also handle parallel and series pumps if you have those in your system. You can do that changing this curve type here. So now to graph a multi-scenario graph, we're going to save this and we're going to save it as our pump versus system template. Great. So now we can always reload that. We could go into our other scenarios and load that same graph, and it should show just the pump system curve for that specific scenario. In our case, we care about all of these different scenarios and we want to show them all on one plot. These scenarios were created just by creating a child and then going in, making the necessary changes. So here we close this left valve, so now all flow goes through here. Here we've adjusted the pump speed down to 80%. So here we can see how that pump curve is going to change. And then similarly with this 120% speed, we can see how the pump curve is going to come out. So now to create our multi-scenario pump system curve, we've created a graph template, which we're going to use for all of our other scenarios. So they're all matching the same flow rate range. We're going to go to File, and we're going to start a batch run. So we want all these different scenarios, and I want to create a multi-scenario pump system graph. So if I wanted to be more selective, I can hit add scenarios, and let's say I only care about the change in speed, or if I only care about the change in system curve. But it's a good idea to run them all, and then you can adjust which curves you're showing later after you load the graph. We hit OK. We'll create it using this template that we've created, and now we'll start our run. So what this is going to do is it gives us the opportunity to see how different system curves can interact with different pump curves without creating specific scenarios with 120% speed with no valves closed, or 120% speed with just the left valve closed, or 120% speed with just the right valve closed. So it reduces the amount of scenarios that you need to check as long as you intuitively understand how a pump system curve operates. So now if we take a look at our graph results, we see some new graphs created from our batch run. Here we can load the pump system curves for each specific scenario. So here we have the 120% speed. We have our 80% speed if the pump is pumping through the right valve only and the left is closed. And then also our base scenario where we see our 50 cubic meter per hour operating point. To show them all on one graph, we can see our folder. We can load a multi-scenario graph, and this is where you can specify which curves that you find most value in. So we definitely want the base scenario. We want to see how our base system and our base pump work, as well as the preferred and allowable operating regions. If we graph the pump curve in the left closed, that's kind of a redundant line because it hasn't changed from here. So we'll go ahead and get rid of these. Similarly, if we graph the system curve for 80% and 120%, no changes were made to the system, so those will match the base scenario. We'll also clean up the preferred and allowable operating regions just so our graph is a little bit simpler. So now it's very easy to see. Here we have our original system curve and our original pump curve operating at 50. If we take our 80% speed pump and lower it in the system, then we have a new flow rate around 35 or 36 cubic meters per hour, or up to 64 cubic meters per hour if we speed the pump up. We can also see how those change if we close the left valve. So if you understand pump system curves and it's very intuitive to understand and explain, then this is a very viable solution to try to condense a lot of different information. And so that's pump system curves in a nutshell. We have some other methods to create them. Again, those are detailed in that blog, which is attached in the webinar as a handout. Definitely worth a read and worth checking out the blogs on our website. So now, taking a look at our pump system curves, how we can read those and interpret the results so we're not creating a bunch of unique combinations within our scenarios. That kind of concludes the steady state analysis that we're going to look at in this webinar. The remainder is kind of transient analysis and how we can look at variables changing over time. If that's something you're not really into or you don't really investigate with your company, now may be a good time to step out, but it's always worth seeing what AFT can do, taking a look at transient analysis especially, which I find most interesting personally. So the first transient analysis we want to take a look at is a profile animation. So if a picture says 1,000 words, animations are probably saying trillions, if not quadrillions. Who knows, 24 frames a second, that's a lot of pictures. So here's a profile from a transient event where we are taking our flow rate system. We have a pre-pressurized line and we're going to be opening all of these spray discharges. So the line is pre-pressurized, it opens, and then flow rate begins coming out of those sprays. Here, if we look at our presentation, we can see the maximum static pressure. So this is when the line is completely full and zero flow. And this is kind of the operating flow rate that we'll see. Or this is the steady state static pressures that we'll see. Similarly, we have our max flow rate, which occurs at steady state, and our minimum flow rate, which is when all of the sprays are closed. So this can be intuitive if you understand the system and you really get the transient interactions. But once you start seeing kind of strange results that you may not intuitively understand, that's where animation can really help. So if we take a look, here's an animation of that same transient event with our initial steady state with the valves all closed, and we're going to open them over the course of 1/4 of a second. So we can see the valves instantly open, our pressures drop, and then we start seeing flow rate through the system. So we can see how that flow distributes through our different profile graphs. This is especially useful when I do water hammer analysis, so you can see how pressure waves transmit through systems, but it's making the analysis much more intuitive to understand what's happening, especially if there's interacting effects like reflecting waves or multiple valve closures or pump trips based on a criteria. The profile graph can show how it changes over time rather than solely relying on the maximum and minimum values. So to create a profile animation, we first have to create a transient within our system. So here we have all of these valves initially closed, and then our transient is that they open over 1/4 of a second to their full flow rate. I'm not a firewater expert, so this may not be accurate, but it seeks a good example and an intuitive example to do an animation analysis. So now if we go to graph results, we have some additional options. Our first case, we're going to be looking at this profile graph. We're going to be looking at our groups again. So these groups I recreated in Impulse. We have our upper sprays and our lower sprays, and we can generate it the same way, showing our maximums and our minimums. We'll also take a look at our flow rate. So this may be good enough if we're concerned about only peak pressure, but generally it's a good idea to animate the transient and see how the system is reacting. So to do that, we can animate using the solver. What that'll do is it's basically rerunning the solver and graphing the results live. So if we hit run, we can see that it drops pretty quickly. We can change the speed and jump some time steps, which gets some wavy worms. And we cannot adjust the time, so we can't scrub the time in this case. And that's why this animate using output is grayed out, because we don't have the output for each of these intermediate stations. Personally, what I like to do is generate enough output to animate using output. That way I can scrub through the transient how I want and jump ahead or jump back very quickly and very easily. So to do that, we're going to go into our transient solver. One thing that I'll generally do is just go to pipe station output. So here we're only graphing the inlet and outlet, even though some of these pipes may have tens of stations. If you have a really big model, it may have hundreds of stations. So we can select all and change them all to all stations. That'll increase our output file size pretty significantly, and it'll also impact our runtime. So one thing that we can do is focus only on the flow paths that we know we're going to create a profile graph of. So here we can go to special, again our special selection tricks. We can go to selection type, and in this case we're going to use groups to select our pipes. So I want to look at the lower sprays and I want to look at the upper sprays. All of those are selected. Go ahead and hit none first, and then go to groups. Select those lower sprays, select those upper sprays. Okay, great. And now only the pipes that I'm interested in are selected. I can change that to all stations. So it'll hit the runtime a little bit, but not nearly as significantly as changing all of them to all stations. It'll reset our output, and we're going to have to rerun the model. So that's definitely something to consider. If your model takes 40 minutes to run, if you create all stations, it's going to take even longer since it has to write all of that output to the file. But it'll also save you a lot of time if you're doing animations, giving you the flexibility to scrub through the animation as well. So we're about halfway there. Fill the time with talk about the weather. Very nice day in Colorado. It's starting to get cold with the winter. Hopefully you're starting to enjoy the fall weather wherever you are, unless you're in the southern hemisphere and you're starting to enjoy spring and your summer. So now we're at 100%, 45 seconds, not bad. We'll take a look at our graph results. And here's an example where I could have saved my graph and would have saved me a little time. So now when we generate, again, we have our max and min, and now we can graph using output. Great. So if we remove our maxes and our mins, now we can run it and it'll graph using output. We can change the speed and not worry about any wiggly worms or anything like that. And we can also scrub through the transient itself. So if I know a transient doesn't start until 5 seconds into the system, while it would be wise to change your system and improve the runtime, now you can just scrub to that point. Or if you know a transient event happens at this time, you can scrub immediately to that point as well. So that's animations. That's how you can change your pipe output to allow you to graph profiles based on output, which is generally my recommendation and generally my approach when I'm doing transient analysis. So you can feel free to quote this in your next meeting. Your animations will say trillions of words. The next thing we're going to look at is a transient graph. So this is how a parameter is going to be changing over time. So this is the spray mass outflow. So as it approaches steady state, it's very easy to see it reaches full steady state within 1 second. It may be good if you have a necessary response time where it has to meet this flow rate in this amount of time. So to do that, we'll go back into Impulse. We'll take a look at this transient junction, and here we'll graph some spray discharges. So we'll look at the upper spray and we'll look at the lower spray. You're going to generate and show how those are comparing. Similarly, we can show some other variables. For sprays, it's a little bit more restricted, but valves are especially interesting. Here we can look at the integrated mass flow rate. So if we need to supply 10 pounds of water within the first 2 seconds of opening, then we might have met that criteria. We can also create similar transient pipes graphs using pipe sections rather than junctions. So here we could look at the difference between one of these end pipes. We can look at the inlet and one of these more intermediate pipes, or we can look at the inlet as well. So here we can see how the static pressure response is. It sees that initial drop as a transient wave before it starts to recover as that flow rate picks up, and then finally approaching the steady state. Something we can do as well is show multi-scenario graphs. So you can create multi-scenario profiles, junctions, pipes. It'll require output, but if you click multi-scenario, then you can just select the different scenarios that you have graphed. So that's another way to do very quick comparison rather than trying to extract the data to Excel and making plots of your own. So those are transient graphs, very quick. And then finally, we'll take a look at a color map animation. So this is something specific to Impulse where we can animate a visual report. So we can take our color map and we can see visually how these parameters are changing in the context of the system. So this is especially useful with water hammer analysis if you have reflecting waves and that might be the cause of your weird pressure spike. So showing it with a visual report, that'll show that reflection where a profile graph may not. And so largely it's focusing on the behavior of the system, though you lose resolution of the quantities themselves. So back in our model, this will be the easiest of them all. If we go to visual report and click animate, now we can select our parameter. And we could just hit show. We're actually going to scale it again because we want to show more resolution at our lower flow rates. So we'll say a maximum 125 gallons per minute. That's going to be our final color. So here we have our legend and we have our time. You can also record these animations and include them in your presentations. So it'll export as an MP4 file, I believe. So now if we hit play, we will see how over a quarter of a second, these should start going through. If we pick the speed up a little bit, you can see how the flow rate increases first through here, then it distributes throughout the piping system. So taking a color map, taking it the next step to visual animation to see how flow is developing through the system. You can also take a look at things like pressure and see how pressure waves are transmitting through the system as well. So something else you should do is include all stations, and that'll give you even finer resolution on how these colors are changing. Great. So building on that foundation, animating profile graphs, animating visual report, a lot of the same processes, but can provide much more intuitive analysis nonetheless. So we took a look at our visual report animation, easily the simplest of them all, and personally one of the most eye-catching in my opinion. Now we're going to wrap up the webinar with 2 minutes to spare. We'll go through a quick summary. So profile graphs, especially useful to show parameter changes along a path. Again, remember those selection tools where you can select the shortest path. Multi-scenario pump system curves, those can save you a lot on creating scenarios, but it's also useful to ensure a pump is staying near its intended operating point under a lot of different potential operating conditions. Visual report makes it very easy to associate data with the location in the system, so really giving itself context to the results rather than just looking at output, seeing a big number, and then looking it up in the workspace. Visual report can summarize that for you as well and make it more intuitive to analyze or explain. Transient graphs, touched on towards the end, showing how a parameter changes over time. A lot of those same things with multivariables or stacked graphs, a lot of those can be done similarly with these transient graphs. And animations, while a picture can show 1,000 words, an animation can show trillions. So it shows snapshots over time, and can show how a behavior occurs, like a transient event passing through a system. It makes it much more intuitive than solely interpreting maximum and minimum graphs. So that's about everything I wanted to cover, just in time with 11. If you guys have any remaining questions at all, always feel free to send me an email at nickvastine@aft.com. I'll always do my best to answer them. Usually you can expect a response within a day. If you have ideas for future webinars, we're always looking for new topics, especially with the new year. We're taking a look at the webinars we want to do for 2021. So now is a prime opportunity if you have ideas about what webinars you want to see going forward. Hopefully this was a good use of your hour. Hopefully you learned a lot about our visualizing tools, so that way you're not relying solely on output. You can build templates, build graphs, make visual reports, customize your output with design alerts, and hopefully make your analysis a bit faster and less tedious. Thanks again for attending, and I hope you have a nice rest of your day. Thanks again.